Good morning, everyone. My name is Aditya from Bsc Chemistry Honors Final Year. I am today here to share my video on visually impaired on the topic of NMR spectroscopy. Let's start with the introduction. During the last 6 decades or so, spectroscopic methods such as UV, infrared, nuclear magnetic resonance, and mass spectrometry have emerged as powerful tools for the identification and structure determination of organic molecules. The ultraviolet and infrared spectroscopy have already though been discussed in detail. Therefore, in this unit we will discuss about the NMR spectrometry which are discovered by the Felix Bloch and Edward Purcell in 1946. Now, what are magnetic properties of nuclei? Like electrons, the nuclear particles, protons, and neutrons are also considered to spin about their axes. Further, like electrons, each proton and neutron has a spin quantum number of 1 by 2. If the protons and the neutrons in a nucleus are not paired, the nucleus as a whole will have a resultant nuclear spin 1. The numerical value of this nuclear spin quantum number is 1 depends upon the number of protons and neutrons having the parallel and anti-parallel spins. It is related to the mass number as shown as below. If the atomic mass is odd, the atomic number is even or odd and having the nuclear spin as 1 by 2, 3 by 2, 5 by 2, etc. In aggregate, with the general rules, nuclear spin such as 1 of hydrogen proton, which is such as 1 3 of hydrogen with protons number 3 and carbon with number of protons as 13, etc. all have the spin is 1 upon 2. Similarly, nucleus such as helium, carbon, oxygen and sulfur have the spin is 0. It is fortunate for the organic chemist that 6 carbon 12 and 16 carbon oxygen are non-magnetic, otherwise the NMR spectra of organic molecules have such been more complex. Nucleus such as of deuterium and nitrogens having the spin is 1 and that of boron is 3. Now since the atomic nucleus is associated with the charge, therefore like any other rotating charge, it generates a magnetic field along the axis of its spin. Therefore, such a nucleus behaves as a tiny bar magnet and has the characteristics magnetic moment mu. Now, nuclear spin states. When a nucleus having the spin more than 0 is placed in an external magnetic field, it is found to we have a set of discrete orientation with respect to the applied magnetic field. These values oriented are referred to as the spin state. For example, for a nucleus with spin quantum number more than 0, there are 2i plus 1 allowed spin states which differ from one another by unity. The various spin states are given by minus I plus 1 up to plus I. Thus, it follows the nuclear spin states like electronic and vibrational states are quantized. For example, a proton with I is equal to 1 by 2 has allowed 2 spin states, that is 2, 1 by 2 are designated, and minus 1 by 2 and plus 1 by 2. For chlorine with spin is equal to 3 upon 2, there are 4 allowed spin states, that is 2, 3 by 2 plus 1 up to 4 designated as. Now let's discuss about the principle of nuclear magnetic resonance of NMR. To understand the principle of nuclear magnetic resonance, let's consider the motion of a common spinning top. When the spinning top is disturbed a little, its spinning axis will trace out a circle perpendicular to the Earth gravitational field such as shown in the figure. Such a motion is known as precession. In a similar way, when a nuclear magnetic is placed in an external magnetic field, it experiences a torque force perpendicular to the axis of the nuclear magnet, which will tend up to align with the field. Since the nuclear magnetic is spinning, it will not align the external magnetic field but will precess around precess frequency. The frequency at which a proton will precess will depend upon the strength of the applied magnetic field. Stronger the applied magnetic field, higher is the precessional frequency. 60 million cycles per second is the applied magnetic field, or in the Gauss it is 14,100. Since a proton has two allowed spin states, that is plus 1 by 2 and minus 1 by 2, it can precess in two principal orientations, one aligned with the applied low and second with the other opposed to the applied magnetic field as shown in figure 2.2. It is possible to induce transitions between these two orientations by irradiating the precessing nuclei with radio waves. When the precessional frequency of the nucleus is exactly equal to the frequency of electromagnetic radiations, the absorption occurs and the nuclei in the lower spin states flip to the higher spin state. When this occurs, the nucleus and the radio frequency beam are said to be in the resonance, and since this resonance is due to the magnetic properties of the nuclei, and it is called NMR, that is nuclearic magnetic resonance. PMR spectrum. Original of the signal. In principle, a PMR spectrum can be obtained by placing a substance containing a hydrogen nuclei or a proton in a magnetic field of constant strength and passing the electromagnetic radiation of varying frequencies through the substance and observe the frequency at which the radiation is absorbed. In practice, however, it has been found more convenient to keep the frequency of the electromagnetic radiation constant and vary the strength of the magnetic field. At some value of the field strength, the energy required to spin the proton nucleus matches the energy of the electromagnetic radiations. At this stage, the absorption occurs and a signal to be observed. Such a spectrum is called as PMR spectrum. The PMR spectra is a plot of the intensity of the absorption along y-axis against the magnetic field and along the x-axis. Y convention, magnetic field strength increases from left to right across the chart. Since the magnetic field through the frequency is denoted by the equation that is mu h naught upon hi is equal to gamma h naught upon 2 pi. The position of any absorption signal along the x-axis can be expressed in either field or the frequency units. A typical NMR absorption is shown in the figure 2.5. Now, what is NMR spectrometer? We have discussed above that there are two ways to scan an NMR spectra: by keeping the applied magnetic field constant and changing the frequency radio frequency oscillates, or by keeping the frequency of the radio frequency oscillator constant and changing the magnetic field. In practice, NMR instruments which work at constant radio frequency and are used since they are easier and cheaper to construct. Such instruments are called continuous wave or CW spectrometers. The schematic diagram of the CW NMR spectrometer is shown in the figure 2.6. It consists of the following part: a powerful electromagnet whose strength can be varied, a radio frequency generator, a detector which monitors the absorption of energy and amplifies the electric signal, and a recorder which records the spectrum on a chart paper which is called calibrated in frequency and ppm units, and a 5 mm wide long sample tube. Schematic diagram is shown in figure 2.6. Solvents used in the PMR spectroscopy. Any solvent which does not contain the proton can be used in PMR spectroscopy. The most widely used solvent is called the deuterated chloroform chloride. Other solvents which are commonly used are carbon tetrachloride, deuterated acetone, deuterated dimethyl sulfomoxide, deuterated benzene frequency. Trifluoroacetic acid is also used sometimes, even though it contains a proton. The reason being that The acidic protons absorbs at a very low field and hence it does not interfere with the absorption of the most common compound which are commonly used in the range of 0 to 10 lambda. Number of signals, equivalent and non-equivalent protons. We have discussed above that in a given molecule, protons with the different environments absorbs at a field strength of different, while protons which have the same environment absorb at the same applied field strength. A set of protons are said to be equivalent if they have the environment and non-equivalent strength. A set of protons is said to be equivalent if they have same environment and non-equivalent. The number of signals in an NMR spectra tell us that how many different set of the equivalent protons or how many different types of protons are present in a given molecule. In most of the cases, it is possible to predict the different types of proton present in a molecule simply by looking at the same structure. But this is not always easy. Thus, we must devise a method by which we can accurately tell it that different kind of protons are present in a molecule. In this method, we imagine that each of the hydrogen atoms or protons is substituted by some other atom. If the substitution of either of the two protons by Z gives the same number of n-isomeric products, though two protons are chemically equivalent, otherwise not. It may be noted that in general, chemical equivalent protons are also magnetic equivalent and thus give rise to the same signal in the PMR spectra. Let's now illustrate this method by few examples. The molecule of the ethyl chloride contains 3 methyl and 2 methylene protons. Replacement of a methyl proton would be ZCH2CH2Cl and replacement of the methylene proton will give CH3CHZCl. These are obviously different products, therefore methyl protons are not equivalent to methylene protons. However, it may be noted that the 3 methyl protons are equivalent amongst themselves since the replacement of any of the same product. On the other hand, the replacement of either of the two methylene protons would give one of the two isomeric enantiomeric products. Such pairs of the protons are called as anisotropic protons. The environment of these protons are mirror images of each other and are magnetically equivalent to each other and thus give rise to the signal. If the PMR spectra is scanned in a chiral solvent, however, in a chiral solvent, the two protons would be magnetically and non-equivalent would be the two signals. From the above discussion, it follows that ethyl chloride contains only two types of proton and thus give the two PMR signals. Proceeding in a similar way, we can easily predict the number of different types of proton present in the following molecules. Let us now consider a molecule of 2-bromopentene. It has 3 methyl and 2 vinylic protons. The 3 methyl protons are obviously equivalent among themselves since replacement of each one or them gives the same product. On the other hand, replacement of either of the two vinylic products of a pair of distereomeric products. The positions of a signal shielding and de-shielding. We have discussed about that the number of signals in a PMR spectrum tell us how many different type of protons are present in a given molecule. In a similar way, the position signals of tells that what kind of protons they are. In other words, the position of the signal tells us the actual environment of the various protons and thus indicates the nature of protons, that is, whether the protons are aliphatic, aromatic, vinylic, acetylene, or are adjacent to the heteroatoms such as oxygen, nitrogen, sulfur, halogens, etc. When a halogen is placed in a magnetic field to get the PMR spectrum, the applied magnetic field causes the circulation of the electrons surrounding the protons. The circulation of the electrons produces a secondary magnetic field and is called induced magnetic field. The induced magnetic field may either oppose or reinforce the applied magnetic field. For example, the circulation of electrons in a sigma bond surrounding the protons generates an induced magnetic field which opposes the applied magnetic field. Chemical shift. The shift in which the position of PMR signals resulting through the shielding and deshielding by circulation of electrons in chemical bond is called as chemical shift. Proton off is the most of the usual types of organic compounds and absorb over a range of 700 Hz as a field of strength 14,100 Gauss. At this field strength, protons absorbs at a frequency of about 60 multiply upon 10 की power 6 Hz. The shielding and deshielding of protons by electrons produce very small changes, that is 1 in 10 की power 8 in the strength of the applied magnetic field. These small changes in the magnetic field strength can't be determined accurately. Consequently, the absolute proton of the PMR signals cannot be obtained from the instrument, as is the ease with the UV and IR spectrometers. However, relative proton frequency is readily determined with an accuracy of about plus minus 1 Hz. Hence, a chemical shift of proton expressed in Hz or CPS with respect to a particular standard. Units of a chemical shift. We have stated above that chemical shifts are expressed in Hz as the difference in the frequency of absorption of a particular proton in an organic compound and the protons of the reference compound. But if we know the chemical shift is proportional to the strength of applied magnetic field or radio frequency used in the instrument, since different NMR spectrometers have the applied magnetic field or the radio frequency used in instrument. Since there are different oscillator frequencies such as 40, 60, 100, 200 MHz, it is desirable to express the chemical shift in some units which is independent to the field strength. The most commonly employed is parts per million, that is ppm. Here we have some characteristics protons in chemical shifts. For cyclopentane it is 0 to 2 and in the tau and tau scale it is 9.8. Factors affecting the chemical shifts. First of all, let's discuss about the inductive effect. The proton chemical shifts of the very simply with the increase in the electronegativity of atom attached to carbon atom bearing the hydrogen atom increases. This is due to the reason that -I effect of the electronegative atom decreases the electron density around the proton, which causes the deshielding. Thus, at higher the electronegativity, higher the deshielding and higher the value of chemical shift. Second is anisotropic effects. We have discussed in section 2.8 the circulation of the pi electrons may either shielded or deshielded a proton depending upon its location around the pi electrons. Such effects, which depends upon the orientation of protons relative to the induced field, are called the anisotropic effects. Thus, mainly due to the anisotropic effects and the particularity of the sp2 hybridization, the olefinic and the aromatic protons are much more deshielded than the protons on a sp3 hybridized atoms. Thus, the aldehydic protons appear more further downfield than the aromatic compounds due to anisotropic effects and partly due to the -I effect of electronegative oxygen atom, which further reduces the electron density around the proton. Third factor is the hydrogen bonding. Proton which exhibit the hydrogen bonding show the variable absorption position over a wide range. Thus, hydrogen bonding decreases the electron density in the OH bond and therefore a proton involved in the hydrogen bonding and get it the deshielded. Further, stronger the hydrogen bond, more deshielded is the proton. The extent of the hydrogen bonding, however, depends upon the predominates depend on concentration, temperature, and nature of solvent. The physics the now we have an example that how the PMR spectrometry can be used to distinguish between ethane, ethylene, and acetylene. Each of the compounds contain only one type of proton, and hence each compound would show only one type of signal. Hence, the chemical shift of three would be different. The proton of CH bond is saturated compounds and are shielded highly. Hence, shows one signal at 0.9 delta. The circulation of pi electrons in ethene produces induced magnetic field which reinforce the applied field at the proton, and hence the ethylene protons are deshielded and produce a signal around 5.3 delta. The circulation in the pi electrons in the acetylene produces an induced magnetic field which opposes the applied magnetic field at a proton, and acetylene protons are shielded relative to the acetylene protons and produce at a 2.5 delta. Now let's discuss about the rule for spin splitting of the proton signals. In general, the following rules are quite helpful in predicting the spin splitting of the proton signals. First of all, splitting of a proton signal is only caused by the non-equivalent neighboring or vicinal protons, that is, protons on the adjacent carbon atom. Second is the splitting of one proton another on the same carbon atom. The number of peaks into which a given proton split is equal to one or more than the number of vicinal protons. In other words, the multiplicity of a proton is generally be given by the rule n plus 1, where n is the number of vicinal protons. The applications of PMR spectroscopy. Identification of substance. Like IR spectrum, PR spectrum can also be used as a fingerprint of the substance. If the PMR spectra of a given sample is exactly same as a known compound, the given compound must be identical with the known compound. In this way, PMR spectroscopy can be used to establish the identification of the substances. Second is determining the molecular structure. PMR spectra are often very complex, but this complexity is not a disadvantage, but it is often useful in the determining the molecular structure, since the spectra characteristics further. Even the more complex spectra can be made interpretable by using the techniques of the deuterium labeling and double resonance. Identification of the reaction products. Whenever is a reaction, two or more products are theoretically possible. PMR spectroscopy has been widely used to identify the actual product. For example, in addition of a HCl to the I-methyl cyclohexene can in principle yield either a product of first or second. Distinctions of between the geometrical isomers. PMR spectroscopy